initially I put the recording, then I paused it, then I forgot to start it. Now it's recording, right? Okay. So measure the qualitative and quantitative analysis. In the instrumental method, we can both use the measurement by measuring the physical or chemical properties of the analyte. In that case, when we use the instrumental methods, we either measure the conductivity or electrode potential, light absorption, light emission, or mass to charge ratio, and fluorescence. Those are the things, physical properties we can measure while we are doing the instrumental methods. And you can see these measurements are beyond human perception range. So there's no way using our senses, we cannot measure the conductivity, we cannot measure electrode potential, light absorption, emission, fluorescence, or mass to charge ratio. There's no way we can measure it. So we really need some devices for this one. So unlike the classical method, the instrumental method is beyond the human perception range, right? So that is the main differences between the instrumental methods and the classical methods. Now let's move to some basic components of the instrument. So here, when we use instruments for the analysis, these three main components are available. Very first thing, we should have the system that we are studying. So this is the system we are interested in. So it is the analyte. The analyte is present in this system. So we simply say this is the sample that we are analyzing. And then it should have the stimulus or the energy source. We will give some energy using the source. Suppose it's a light radiation. So there should be an energy source. And then we pass the signal through our system and it will generate a response. So the response is the analytical information that we are interested in. Based on the system, we can determine the either, let's say, concentration or whatever the things in the system that we interested in. For example, let's say an example in the UV. We have the sample and we irradiate it using a light source, and then when the light passes through the sample, it either absorb, scatter, or reflect light. Then the remaining light which is not absorbed or scattered will pass through the sample and it will go to the detector, and then here the detector will give some UV spectrum. That's an example. We will do it in more detail under optical spectroscopy section. Don't worry about this right now. So this is the main component in the instrument. So the energy source, it can be electromagnetic signal, electrical, mechanical, or nuclear stimuli. So it can be any of these things, right? And what is happening here, the instrument converts information about the physical or chemical characteristic of the analyte to information that can be manipulated and interpreted by human. So what is happening here, when we have the instrument, this instrument, it converts the physical or chemical characteristic of the analyte. So whatever the characteristic, physical or chemical characteristic of the analyte into the information that is measurable or understandable by human. So by simply, let's say we have some colored compound, and we cannot, by just looking at this compound, we cannot determine the concentration. What is happening in the UV, when we pass the light radiation, and it gives a response, the signal, and that signal, based on that signal, the UV spectrum, we can determine the concentration. So that spectrum can be interpreted by human. So that is the main duty of an instrument. So it converts the information, any physical or chemical information in the analyte to the data that can be interpreted by human. Okay, so therefore we can say this analytical instrument is a communication device between the system and investigator. It acts like a communication device. So it helps us to get an idea about the analyte or the sample that we are interested in. We can communicate with the sample using the analytical instrument. All right. Next, here this table lists some types of instrumental methods available. So as I mentioned in the previous slide, the electromagnetic, there are some electric processes, electromagnetic, electrical. Okay, I think some of you have Chairuani, can you please mute your phone? Yes, thank you. Okay, so there are this slide summarizes the types of instrumental methods available. So the types of signal can be the electromagnetic radiation, electrical, mass, reaction rates, thermal or radioactive. These are some examples of the signal type. And you will not learn all these examples under the analytical chemistry course, but to certain extent you will learn all these things maybe under the advanced analytical chemistry course 1 or 2. So, and here I just listed the example. So when we use the electromagnetic radiation, it can be either absorption, emission, scattering, refraction, diffraction or rotation. So the emission in the atomic emission spectroscopy, emission is using, and the absorption and scattering in the Raman spectroscopy, refraction spectroscopy used refraction methods, and X-ray diffraction and CD, circular dichroism spectroscopy use optical rotation. And similarly, the electrical things, pH electrodes, you know, we use voltage and coulometry, voltammetry, impedance spectroscopy. So impedance one you will learn under electrochemistry. So all these things are the methods and the types of signal, and the mass and reaction rates under kinetics method, and the DSC, differential scanning calorimetry, and the Auger alpha particle. Auger electron spectroscopy you will learn, but I'm not sure whether you will learn this electron neutron activation and the alpha particle one, but I think it's worth to read and get some idea about how these instruments work and for what instances we have to use these instruments. Okay, sorry. Here, this is the block diagram of all instruments, right? All instruments have signal generator, and signal generator, it can be a chemical sample or the radiation beam, and transducer or detector. So transducer, we will learn this in detail later. Transducer, what transducer do is it change the energy from one form to another, right? For example, electricity to voltage, the current to voltage, light to electricity, or light or heat to electricity, particles to pulses. Like this, it transfer some energy, like it's doing the energy change. We will discuss this in detail in the all the transducers and all these things. And the signal processor. Then after the transducer convert the energy, there's a signal processor and it processes the signal. The analytical signal, it either filters some unwanted things or amplify the things or modulates, or it attenuate any of things. All these things will be done in using a signal processor. Then after the instrument process signal, then it goes to the output device. Then the output device, it can be a computer, any meter, so anything. It will give us some numerical value or a graph, whatever the things, that is the output. Most of the cases, computers are available as the output device, but that is what is happening in the instrument. But it gives us the data. Data does not have any knowledge. There should be someone with the knowledge and the intelligence to interpret those data. Once we get the signal or whatever the data from the instrument, there should be someone to interpret data. Otherwise, the data will not be useful. We should have some person who is capable of interpreting this data. Okay, so here it says the analytical signal arises between the signal generator and transducer. So the transducer, or it generates the signal, and the transducer produces a recordable event such as an electrical or optical signal. So as I mentioned earlier, transducer convert the signal into another form. So that one is recordable. And this transducer part, don't worry right now. You will understand more about this one when we do the transducers. So what you have to do, this is the, you have to know any instrument should contain these basic components. So that is the block diagram for all instruments. Okay. Okay. Then how the information of interest can be represented or transformed. Now suppose we have instrument, and I told you it convert the required the information to whatever the way that we can read and understand. But how it happens? In the instrument, there should be a way of transporting things. Because in the analyte, it has some physical or chemical characteristic. Then we just get a number or graph or anything, at the end. So what is the way this information is transferred? So therefore, it is important to understand how, before we understand how the instrument functioning, we have to have an idea about how this instrument information can be encoded or represented by the physical and chemical characteristics. So before investigating, let's see how it can be encoded or represented. In that case, data domain, we call something like data domain, that is the various methods of encoding information. Data domain is the various modes of encoding information in the instruments. So here, this diagram shows the data domain. In the data domain, there are basically two main types: electrical domain and non-electrical domain. So either electrical or non-electrical domain, we can represent the information. We can transfer information. Look at the non-electrical domain. The non-electrical domain has physical and chemical domain, scale, position, number. So whatever the characteristic, physical and chemical characteristics that we are interested in sample, it falls under non-electrical domain. And then at the end, let's say we will get a number or any signal, digital or analog number, any signal. So that is also under non-electrical domain. And the electrical domain, the bottom part, it can be further categorized into analog, time, and digital. So analog domain, time domain, and digital domain. Under the analog domain, current, voltage, charge, those are the examples. And the time domain, frequency, pulse width, phase. And the digital domain, count, serial, parallel. Look at here. Not only the electrical domain, but the number. Number is a non-electrical domain, but number is also a digital one. So keep in mind, under the digital domain, here the number is also, even though it's a non-electrical, number also goes, should be categorized under digital. Right? So in the instrument, whatever the instrument, normally the information transfer within these domains. So suppose we have any physical characteristic. So that is a non-electrical. Data transfers from non-electrical, starts from the non-electrical, and then at the end, it will give the number. So that is also non-electrical. But in between, it will undergo any current change, voltage change, or pulse width change, frequency, whatever the change. So normally what is happening, non-electrical domains converts into the electrical domain, and then again it at the end we will get a signal which is in the non-electrical domain. I hope it's clear. Okay, let's little further clarify that using this example. So how this data information transfer from the electrical to non-electrical thing. So for example, here suppose we have tonic water sample. So in this we will do some whatever the fluorescence analysis, and fluorescence analysis, let's say fluorescence analysis of analyte A. And what is happening, as the signal will in the energy source will give a laser pulse to the sample. Then here the fluorescence analyte will absorb this laser pulse and it will emit fluorescence signal. So that fluorescence emission signal is proportional to the analyte present in the tonic water, right? Then that fluorescence emission signal, it will go through this optical filter. There's an optical filter. It will go through the optical filter, and it will filter out any unwanted signals, and it can only further process or further transfer the wanted or interested optical signal. And it will go through the phototransducer. So the phototransducer, what is happening in this phototransducer, it transfers that fluorescence energy into current. Ci is the current. It transfers the fluorescence energy into current, and then there's a resistor using V equals IR, Ohm's law. Then the current converts into voltage. And there's a digital voltmeter. It will give the number of the voltage. So 4.1, that is in the non-electrical domain because it's a number. So that one, using this number, we can have an idea about the fluorescence intensity. Then we can get an idea about the analyte concentration. Okay, here, let's see, look at this one. So this is how the information flow. Source intensity, that is the laser. Then fluorescence intensity of analyte. Here, the analyte has certain fluorescence intensity. It converts into electrical current, I. So here the source intensity to fluorescence intensity, all these things governed by the laws of chemistry and physics, and the fluorescence intensity will be converted into current using the phototransducer, and then the electrical current will convert into voltage using Ohm's law. And then using the meter transfer function, whatever the meter transfer function, the voltage will give as a number, right? So here, what are the data domains involved? First, it has the fluorescence, then it undergoes some of the current and voltage, again a number. Can anybody tell me what are the types of domain? I'm asking whether it's electrical or non-electrical. We have fluorescence intensity and the current and voltage, and it will give us a number. What do you think? Which type of domains? Okay, tell me fluorescence intensity. Is it electrical domain or non-electrical domain? Let me go back to the here. Okay, by looking at this circle, fluorescence intensity, is it non-electrical or electrical domain? No idea?
Electrical domain.
Fluorescence intensity. Fluorescence intensity, when it says fluorescence intensity, it is a physical property, right? So it goes under the physical or chemical characteristic of the signal. Therefore, that one we can convert under non-electrical domain, because initial physical or chemical characteristic of the analyte, those things we categorize under non-electrical domain, and then it converts that physical characteristic, which is fluorescence, that one we convert you to current and voltage using a photo transducer. Then current and voltage, it comes under the electrical domain. And at the end, some readout device like the voltmeter will show a number. Then it is again non-electrical, right? So intensity, it is non-electrical. Then it undergoes the current voltage, and again at the end it gives the number. So it is also again non-electrical. That is the normal way of how the instrument happens. Normally instrument starts from the non-electrical one, and then electrical domain, and again final output will be non-electrical. So the measurement process starts and ends in the non-electrical domain, and the measurement go through electrical domain. That is the normal way of any instrument. But when we measure the signal, or when we do some analysis, it can be completely non-electrical domain too. The measurements can remain completely in non-electrical domain in certain cases. For example, suppose we are measuring the volume of some, let's say we are measuring the volume of a cube using a ruler. So we have to take height, width, and the length. So when we do the measurement, first we have this cube. So it starts from the non-electrical domain, and then we measure the length. Again, it gives the number. So as an output also, it gives the number which is in non-electrical. So in that case, it can be completely non-electrical domain. And if we, another example of how, let's say we are measuring some weight of a sample. So using some physical properties, we can extract the sample, and we use a scale, simple balance, to measure the weight. Then it doesn't involve any electrical domain. So it also completely non-electrical. So there are certain cases, some measurements which can remain completely in non-electrical domain, but normally the measurement in the instruments, measurement starts and ends in the non-electrical domains, and it goes through the electrical domain. That is the normal way. Okay. Is that clear how to identify these things? I hope. Yes. Okay. Okay. And then here, before move to next section, I would like to give some examples about the instrument. Therefore, I'll roughly cover, tell you what is known as detectors, transducers, and sensors. But as I mentioned earlier, the transducers, we will learn it in detail under optical spectroscopy part in a later day. But for right now, what are the detectors? So this is the definition of the detector. You can read it. So it mechanical, electrical or chemical device, it can identify or record or indicate one of the variables in its environment. It can identify, actually simply it can identify things, variables. So this is the definition of the detector. So detector, normally it detects the signal. The signal can be any change of the variables such as pressure, temperature, electrical charge, electromagnetic radiation or particulates or anything. It detectors detect the changes in different forms. So there should be a detector in any instrument. Detectors are available. And the transducer, so as we discussed earlier, this transducer converts information. So it converts information in non-electrical domains to electrical domains and converts in the other way. So photodiodes and photomultipliers are some examples of transducers. We will discuss later. We will discuss this later in detail. And the sensors. And most of the cases, there are sensors. So sensors, it can be the biological sensors, chemical sensors, but we are interested in chemical sensors. So it also kind of detector, but it is a device which can have which has ability to monitor specific chemical changes. Like very good example is the glass electrode, the pH electrode. So it changes once the concentration of ions are changing, it can easily sense the change. And the readout device is the must, because in the instrument there should be a readout device. That is how we get the signal, how we get the output. And in the readout device, it has a transducer, output transducer. There are transducers called input transducer and the output transducer. Output transducer transfer the information which is in the electrical domain to any understandable signal from to the human. So that is the output transducer. So that is the readout device. So those are the examples of those instrumental components, and I took this from this book, directly from that textbook. You can refer this one. So for example, if we have let's say the pH meter, that is the most common and very good example that we all know. So that is the instrument, and as the source, it has the glass electrode. It senses the activity of the ion, and the information that we get is the hydrogen ion activity. Normally we call as sensitivity, the concentration, but the correct term is the activity of the hydrogen ion. And then it using the glass electrode, it absorbs hydrogen ion. So the glass electrode is kind of information sorter. And then input transducer is the glass calomel electrode. So here the hydrogen ion activity converts into a electrical signal, current, and then voltage. The data domain of transduced information is electrical voltage. Then the signal processor or the readout device, again it transduces this electrical signal it can amplify, digitize this, and then it display. We can have in the display, you know, there's a small display. We can read the hydrogen ion activity. So that is the most easy example, because that one we all know. And also the photometer, atomic emission, coulometer, mass, TC. So all these things, those are the sources of each and every instrument. And analytical signal can be different analytical signal, light beam, UV radiation, and mass to charge ratio, like that. And the information, so to sort information, there are filters, monochromators. We all know monochromators, and cell potential, chromatographic, whatever the things. All these things happen. Same thing happens in every instrument, but only difference is the part we do is little. It has little bit different, but in general, each and every instrument's doing the same thing, right? So this table summarizes some examples of the instrument component. You can look at this one in later and read the scope, so it has much more information. Okay, then calibration of instrumental methods. What do you think? Can we continue, or do you need a break? You need a break, or 5 minutes break?
5 minutes breaks would be fine, madam.
Yeah, let's have a 5-minute break. What's the time now? 11, 12, around 11, 17.
Okay, madam.
Okay, in 5 minutes, just drink some water, and let's be back in 5 minutes. Okay.
Okay, madam. Thank you.
Okay, are you back? All are back. Oh. So Chatrika, are you there? No? Chatura, are you there?
Yes, madam.
Okay. And how about Hamudi? You there?
Yes, madam.
Okay. I just randomly check. Tanu? Tanu. Tanu, are you there? No. And Kanishka. Kanishka or Kanishka? Kanishka.
I'm here, madam.
Kanishka, okay. Piyumi?
Yes, madam.
All right. Vibhasha? Vibhasha? Are you there?
Yes, madam.
Okay, okay. Then looks like all are here. Let's continue. Okay. Then let's move to calibration of the instrumental method. So we got a brief idea about how the instrument, how we can convert this important information to the important information in the analyte to the information that we can manipulate. But before that, it is really necessary to calibrate the instrument. So during the calibration, what is happening, based on the response or based on the response which is obtained from the device, we determine the analyte concentration. Before we determine the analyte concentration, or before we get an idea about the analyte concentration based on the analytical response, we should confirm, okay, the analyte concentration is proportional to the analytical response. To do that, we have to do the calibration. So, can anybody tell me what are the calibration methods that you know? What are the available calibration methods? What is the very common calibration method we perform? How we calibrate things using, let me say like this, using a graph, you can do a calibration. So what do you need to do the calibration? Simple calibration.
We need data, madam, is it?
Yes, we need data. There's a special thing we call, we need standards, right? So that's the very normal basic things that we are doing. We're using the standard. We plot the standard plot. We take standards and we do the take the data. As you mentioned, we need data. We collect data from the instrument and we plot the calibration plot, right? And then once we have the unknown concentration, using the calibration plot and the analytical response of the unknown solution, we measure the concentration. right? That's the really very common thing that we are doing. For example, in the UVs, we prepare standard series and measure the UV measurements and then plot the graph. Then once we have the unknown, we again measure it, collect the data, and determine the unknown concentration. So that is that, even though that's the basic normally what we are doing, that is an external calibration method. So let's discuss available calibration methods. There are 4 types of calibration method. The first thing is the comparison with standards, and the second one, external standard calibration. Third one is the standard addition method, and fourth one is internal standard method. These are the 4 main calibration methods available. Right? Let's discuss in detail about these calibration methods. First one, comparison with standards. So when we compare with standard, it can be either a direct comparison. So in the direct comparison, what we do, we compare the property of the analyte with standards, compare the property of analyte or the unknown sample with a standard. The standard, we know the exact concentration. So that the property, let's say the concentration property being tested matches or nearly matches that of the standard. Let me tell you an example. So suppose we have some colored compound. In the colored compound, we want to determine the concentration using a colorimetry. And what we can do in the direct comparison, we take a standard with the colored compound, but in that standard, we know the exact concentration of the standard. Then what we are doing, we match the standard color with the unknown sample. Suppose at the very beginning, it will not exactly match, right? Then we may have to do some dilution. Then we do a dilution. We should know the dilution factor. And when we do the dilution, then again we match the color of the unknown with the standard. And we dilute the standard sample until the color matches with the unknown. Then we know the dilution factor and we know the initial concentration of the analyte, or not the analyte, we know the initial concentration of the standard. Then using the dilution factor, we can determine the concentration of the analyte. So that is direct comparison. Here we don't do any calibration plot. We are not plotting any calibration. We directly do the comparison using colorimeter. Right? That is the one method, direct comparison. So we compare with the standard. Another most common thing is the titration. That is the most commonly used technique to compare with standard. In the titration, you all know, we take a standard solution and we take the unknown solution, we titrate with the standard, and then we measures the measures and find the concentration by comparing with the standard. So these 2 methods are the comparison. One available it is kind of calibration. So comparison with the standard, direct comparison or titration. The second one is the external standard calibration. That's one we discussed at the beginning. This is mostly used technique. So in the external standard calibration, what we do, we prepare a standard series of solution with the known concentration. So we call it as standard. So we prepare a series of standard solution. Then after we prepare the series of standard solution, measure the analytical signal. And then the analytical signal versus concentration will be plotted. And here you will get a linear graph. When you prepare the standard series and plot the signal versus the concentration of the standard series, you will get a linear graph. This SBL, this is for the blank. So if there's a blank signal, so if there are some background signal or blank signal, you can either correct it, or if you plot, you will have some baseline. So that's okay. But here we will plot the signal versus the concentration, and then this is the standard calibration plot. Now, when we have the analyte with the unknown concentration, what we will do using the same instrument, we measure the analyte signal, unknown signal. Suppose unknown signal is somewhere here, and then using the calibration plot, we can find we draw the line, you know this, we can draw the horizontal line and vertical line to the x-axis and find the unknown concentration easily. That's one way. And also, if you know the equation of this graph, by plotting the, let's say this is y equals mx plus c type graph. So by plotting the y value as the signal intensity, you can find the x value, concentration easily. So by using any of these methods, we can find the unknown concentration. But this calibration method we call as external standard calibration. So in the analyte is separate, the unknown sample is separate, but we prepare standard samples separately. We do not add any standard to the unknown sample. The standard samples are preparing separately. Therefore, we call it as external standard calibration. There's a disadvantage of this method, external standard calibration. What is it? If there's a matrix effect, matrix effect means suppose when the standard has one component A, but in the actual situation, when the component A is present in a sample, other components which will be available in the sample will have some interferences to the analyte signal. So in that case, the analyte signal in the actual sample either attenuate or either it can be changed. But we are not, when we do the external standard calibration, we are not accounting for this matrix effect. So external, when the standard series that we are preparing will be free from any matrix. So there's no any matrix effect. We will prepare those in very pure DI water or pure solvent. Therefore, we will not be able to account for the matrix effect. So if there are matrix effect available, then that's a problem. So we will not be able to get the correct concentration of the analyte, right? So to overcome, that is the problem in the external standard calibration. If you think there can be any matrix effect, the sample, if you think it might have some matrix effect, then what is the best way to prepare the sample? If there's a matrix effect, so we can use standard addition method. That is the third type of calibration. By using the standard addition method, we can minimize matrix effect. I think you are familiar with the standard addition method, but if you are not, I will explain it again. So what is happening in the standard addition method? In the standard addition method, we have unknown solution. So the concentration, we don't know the concentration here. Unknown, let's say it's CX. And we will use standard solution. So in the standard solution also, it's same as the component. The analyte component is same, but the concentration we know exactly, right? So what we will do here? We will prepare again. It's kind like of concentration series. We have to prepare concentration series. To prepare a plot, actually, even with two data set, we can draw a graph, but it should have at least five individual data sets just to prepare a calibration plot. So more the data points you have, you will get more accurate calibration plot. So at least I would say you should have five points when you prepare in the calibration plot. So you may have four is also enough. You can have five data points when you prepare either in the external calibration or standard addition or internal standard addition method, right? So again, what is happening in the standard addition method? We will take, let's say we are preparing sample in volumetric flask, and for different volumetric flask, we will add same volumes of unknown solution. The blue color one is the unknown solution. The volume of unknown solution is same in every volumetric flask, right? Let's say it is Vx, and then the standard solution we will add in different volume. For the very first one, we will not add any standard solution. So no standard solution here. Then one volume of the standard solution, and let's say 5 milliliters. 5 milliliters here, 10 milliliters here, 15 milliliters here. Likewise, different volumes of standard solution to each volumetric flask. Then that means the concentration of standards is different now, right? But the concentration here in the unknown sample is same in all. Then after we add standards and unknown, we will top up the solution. We will top up the volumetric flask to desired volume. If it is 100 milliliter flask, then we'll top up to the 100 milliliter. Then here, when we take the measurement, let's say we are taking UV. When we take the UV absorbance, now the signal comes from both unknown plus standard solution. The signal intensity is proportional to both unknown as well as standard solution, right? So here, this is the calibration plot. of the standard addition. Here ignore this one, x-axis says added grams, but you can take as a concentration, or what grams is also fine. Look at here. When the y-axis is the added grams or added concentration of analyte, right? Here, when there's no added, the first one, first volumetric flask, there's no any added standard solution. So the standard solution concentration here is 0. Then we can plot the signal here. Suppose this is a signal, 5 or 6 or something is the signal. So in that signal, it is the signal of unknown plus background. Background signal is also there. So when the added concentration is 0, that gives the signal of unknown. Then when you go from through the x-axis, here this signal, all other signals are coming from the signal of unknown plus the added analyte or added standard solution, right? So what we can do, the unknown concentration here, to determine the unknown concentration, we can use the equation in the graph, or we can follow the extrapolation method. Extrapolation means when you extend this, it will give the unknown concentration. So I would say just how to find the concentration. Please go and refer the school textbook. It clearly says, because here by using the equation, the signal is proportional to the concentration and the volumes, volume of the unknown as well as the total volume. So using that proportionality and the equation that we get, you will be able to find the concentration. Here we need the slope and the intercept. So it is clearly shown in the textbook. So I highly recommend you to go and refer that and find how we can use the equation and the extrapolation method to find the concentration. If you have any problem in understanding that, let me know. Then I'll discuss it next day. So, but it is simple thing, simple equation. It is not that difficult equation. You first use the proportionality, and then by taking the slope and the intercept, the ratio of the slope and the intercept, you can easily find the concentration. Please go and have a look of the method, right? So that is the standard addition. So when we do the standard addition, we can minimize if there is a matrix effect. If there is any matrix effect, now we can eliminate it, because we are adding these standards to the sample itself. So whatever happens to the analyte, same thing happens to the standard solution. Therefore, the signal, there's no any deviation of the signal. So we can minimize the matrix effect when we use the standard addition. Okay. Then the third one is the internal standard method. Internal standard methods, most of the cases we use this method when we do chromatography things, right? So if we use internal standard method, we are adding standard sample to the analyte. It is same as, it is, don't confuse this with the standard addition method. We are adding analyte to the sample. We are adding standard standards to the analyte, but that standards, it should have identical properties. It should have identical properties to the analyte, but this standard should not be present in the analyte. Let me explain it in using an example. So suppose we are analyzing some blood serum, right? We are doing the analysis of sodium content in the blood. So in that case, we can use lithium as an internal standard. We know lithium is not present in the blood, but therefore the standard is not present in the blood sample, but it has identical properties to the sodium. Therefore, we can add lithium as an internal standard. So when we use the internal standard method, we can avoid sample loss in the workup because we are adding the standard to the sample itself. So we can minimize or completely avoid the sample loss. And also, look at the second point. That is what I explained. Internal standard provides a reference compound. It carefully selected to mimic the chemical behavior of the analyte, to which the concentration and responses can be ratioed to provide a relative response. It says the internal standard is a reference compound. It should mimic the chemical behavior of the analyte as the lithium in the sodium. When we measure the sodium concentration, we add lithium as an internal standard. So lithium mimics the chemical behavior of sodium. And by taking the concentration ratio of the lithium and the sodium, we should be able to get a relative response. So suppose we have a chromatogram, right? And the analyte and the standard will give the peak. I will show you this here. So we have X, the unknown signal. This is S, the standard signal. So the area of the unknown is proportional to the concentration of unknown, or area of the analyte proportional to concentration of analyte, area of standard proportional to concentration of standard. So here, after we divide, this is the rearranged one. Area of analyte proportional to concentration of analyte, right? It should go here first. And when we take the division, we will end up with this equation. And once we know the, once we have this kind of relationship, only thing we don't know is the concentration of analyte. Then by plugging values to areas of standard analyte and the concentration of standard, we can determine the analyte concentration. So F is the constant. It is constant to the instrument. So it is an instrument response factor. So it will be changed depending on the instrument. So here we can easily find the standard, the analyte concentration, right? And third point, internal standard cannot be a compound that might occur in a sample. So internal standard cannot be a compound which is present in the sample. What is happened if internal standard is present in the sample? So then we will not be able to get this relationship, because the signal, standard, internal standard signal, this signal will be due to the standard plus analyte. So if this signal is arising because of the standard and plus analyte, then we will not be able to get this kind of relationship. Therefore, whatever the internal standard we use, it cannot be present in the sample, right? And here we make the fourth point, we have to make an assumption. Whatever happens to the analyte in the matrix also happens to the internal standard. So we have to come with this assumption. By assuming whatever happens to the analyte, the same thing happens to the internal standard, we can perform this calibration. So that is assumption we have to make. Right, so those are the four main types of calibration methods available. So among these calibration methods, based on the situation and based on the instrument, we have to determine, and based on the situation, based on the sample, and based on the sample matrix, and depending on the instrument, by considering all these factors, we have to determine which type of calibration that we should follow, right? Okay, any question so far? Is it clear?
Clear, madam.
Okay, then can we move to the next part? Okay. Okay, so that is about the that is all about the calibration. And then so we discussed the main components and then how the signal arises, and then we discussed, in order to get an idea how, what we should do, how we can perform the calibration, and all these things now we know. But there are different instruments. So before selecting an instrument system, there should be some way selecting an instrument, because when we go to an instrument lab, we have UVVs, HPLC, GC, NMR, all these instruments are available. For a particular analytical problem, there should be a way to select what is the instrument we have to use. So as an analytical chemist, we have to have, before we move on to the experiment, we should have some idea, or we should answer some questions such as how much of instrument, how much of sample is available, what are the desired information that we should know about the sample, and what are the available instrument, because any instrument will not be available. So what are the available instrument, and especially the time, cost, all these things we should pay an attention as an analytical chemist when we select an instrument. Now let's see what we should know, or what we should think, what we should consider before selecting an instrument system. So there are some numerical criteria for selecting an analytical method. We call them as figures of merit. So has anybody knows what are the figures of merit? This is one of the main thing that analytical chemists should know. What are the figures of merit? Any idea? Or you heard it today? You never hear it before?
heard it today, madam.
Okay, okay, good. So the figures of merit, that word you might hear it today, but I will show you what are the figures of merit. These things, these are the figures of merit. I'm pretty sure you have heard this before, but you might not know these called the figures of merit, right? Precision, accuracy, all these things, I know you hear it before, but these figures of merit word is the new thing. That is the new word. So keep in mind, these are called, in analytical chemistry, we call it as figures of merit. So figures of merit are the precision, bias, sensitivity, detection limit, dynamic range, and selectivity. These 6 figures of merits are the most important thing, and you will use it throughout whenever you are doing any analytical chemistry experiment or whatever the thing. You will have to look at these figures of merit. So precision, you can get an idea about the precision using standard deviation, relative standard deviation, coefficient of variation. By using these things, you will get an idea about the precision. And the bias, absolute systematic error, relative systematic. I think we discussed these two in that course. What's the course? The significant figures one, precision and bias, if you remember. We discussed these two, but I will again go through these two. So how to find the standard deviation, you already know this. And the sensitivity of instrument is really important thing. By looking at the sensitivity, we have to select the instrument. So sensitivity can be divided into two: calibration and analytical sensitivity. Let's discuss this in detail. And the detection limit. Detection limit, we will discuss all 6 in detail. I just summarized it here. And detection limit is the blank plus 3 times of standard deviation of the blank. I'll tell you how to find it, how to do the calculation. So the detection limit is also important. So the thing is, that is when we find the concentration, we should have an idea about the instrument response. What is the minimum limit that we can detect using the instrument, right? So dynamic range as well as selectivity. So these 6. Now let's move forward and let's discuss these 6 figures of merit. This is really important. Keep in mind, even when you are, let's say, when you are doing higher studies also, you will learn these things in detail. And when whatever the analysis you do, you have to pay very much attention for these figures of merit. So quantitative instrument performance criteria can be used to decide whether a given method is suitable for attacking an analytical problem. So by using these quantitative, we call them as these figures of merit at quantitative instrument performance criteria. So by using these, we can determine, we can make conclusions whether this particular method is suitable for this particular problem. And other than that, other than the listed instrument performance criteria or the figures of merit, you see, those are the quantitative things. Listed here are some qualitative instrument performance characteristics that you have to pay attention when you select the analytical method, right? The first thing, speed of the instrument, whether it is time consuming or whether it is time saving, that we should pay attention. And the ease and convenience. Always we should go for the easiest method. And the third one is skill required of operator. So if there are no trained person, we will not be able to perform that instrumental method. And the cost and availability of instrument. So the cost is really important, because if we select one method, if it is highly expensive, then there's no point of using highly expensive one if any cheaper method is available. So cost, we have to pay attention for the cost as well as the availability of the instrument. And the per sample cost, same as the cost, that is the cost is the instrumental cost, and also the sample cost also we have to pay attention. So these are sorry, these are qualitative parameters, and the figures of merits are the quantitative parameters. By combining both these quantitative and qualitative parameters, we can determine which type of instrument we should use. Okay. Now let's discuss about the 6 figures of merit in detail. The precision, I already discussed this with you when we are doing this significant figures lecture in the first semester one. And the precision, you know, it is the reproducibility of the result. So we can repeat the measurement, and by repeating the analytical method, we can have an idea about the precision. So normally, any analytical method should be highly precise and high accuracy. So these figures of merit, how we can find the precision, absolute standard deviation, you already know that one, and relative standard deviation, standard error, and coefficient of variation and variance. I think I asked you to remember those equations. So this is, by using these things, we can have an idea about the precision of that particular method. And the bias is the measure of the systematic or determinate error of an analytical method. So we can find the bias by taking the difference between the population mean and the true value. So any instrumental method, the bias should be less biased. So the least biased method should be selected when we select the instrument. And the sensitivity, I think this might be new. The sensitivity of the instrument is a measure of its ability to discriminate between small difference in analyte concentration. So instrumental sensitivity in general, some instrument is, when we say, okay, this instrument is highly sensitive to this particular analysis, that means we can detect even a really small change of the analyte concentration. If we can detect the very small change of the analyte concentration, we can tell that, okay, this instrument is highly sensitive to this particular analysis, right? So whenever we whenever we select an instrument for the analysis, we should go for the most sensitive method. So when we select the most sensitive method, we will get more accurate result. And the sensitivity depends on the slope of the calibration curve and the reproducibility or precision of the measuring device. So the calibration curve and the precision of the measuring device both will account for the sensitivity. By depending on these two factors, sensitivity will be changed. And for example, if the slope, I told you here the slope, sensitivity depends on the slope of the calibration curve, right? Higher the slope, more sensitive the method. So when the slope is higher, the calibration method is much more sensitive. So the higher the slope, the more sensitive the method. Which one has the, so here, which calibration curve has higher sensitivity? Blue or red? Which one has high sensitivity? So in order to tell,
Blue, madam.
blue, yes, blue, good. Because blue has the higher slope compared to the red one. When the slope is higher, the sensitivity is higher. Therefore, the blue graph has the higher sensitivity compared to red one. And the sensitivity, the sensitivity can be divided into two: calibration sensitivity and analytical sensitivity. What is meant as calibration sensitivity? The calibration sensitivity is the slope of the calibration curve at the concentration of interest. So when you plot the calibration curve, you will get, when you get the, you will get equation like this. S is signal equals M is the slope, C concentration, and the SBL is the blank signal. So the slope will give the calibration sensitivity. So suppose you get, you are asking, okay, this calibration plot has been given, and you are asking what is the calibration sensitivity. So in that case, what you simply has to do, just tell the number appears in the slope. That is the calibration sensitivity. You don't need to do any calculation. So if the equation has been given, slope is the calibration sensitivity. But when we report the calibration sensitivity, there's a small disadvantage. It is the calibration sensitivity fails to take into account the precision of the individual measurement. So it is the slope gives the overall measurement, so, right? So we will not be able to take the precision of each and every individual measurement by looking at the calibration sensitivity. So that is one disadvantage of taking the calibration sensitivity. So it fails to give an idea about the precision of individual measurement. So as an alternate, in order to overcome this problem, we can calculate the analytical sensitivity. So when you calculate the analytical sensitivity represented by gamma. So in the how you find the analytical sensitivity is by dividing the slope by its standard deviation of the measurement. We divide the slope by standard deviation of the measurement. By dividing that, you will get the analytical sensitivity. So by using that, we can consider the precision of the individual measurement, and we can overcome the that problem associated with the calibration sensitivity, right? That is how to find the sensitivities. And before move to the detection limit, at the end I have this question. Maybe you can do it anyway, I will pause this one and you can do it later. So in this question, it says the equation has been given and it asks to calculate the calibration sensitivity, analytical sensitivity and detection limit. Detection limit I will explain again. I will explain, but here, calibration sensitivity and analytical sensitivity. So what is the calibration sensitivity? Now the spectrum, the equation has been given. This is the equation. Can anybody quickly tell me the calibration sensitivity here?
1.12.
1.12, good. The calibration sensitivity, when it asks calibration sensitivity, it is simply the slope of the equation, the graph, right? So calibration sensitivity is 1.12, and then when it comes to the analytical sensitivity at 1 and 10, then you have to go to the standard deviation and find it. That one you have to calculate, but it is straightforward. Calibration sensitivity, take it from the equation. Okay, detection limit. I will quickly go through because we have only, it's already 12:10. Okay, let's see. Detection, is it clear so far? I think it's clear, right? Okay, detection limit. Detection limit is the minimum concentration or mass of analyte that can be detected at a known confidence level. Minimum concentration or mass of analyte. So that means when it comes to the detection limit, that is the minimum concentration. Let's go from the concentration. That is the minimum concentration that can be detected using that particular instrument, right? This limit means detection limit depends on the ratio of the magnitude of the analytical signal to the size of the statistical fluctuations in blank signal. So you will get an idea about this when we talk about the signal to noise ratio. So, and this detection limit of any analytical instrument depends on the blank signal, right? Blank signal, and if the analytical signal is not larger than the blank signal by some multiplication, it is impossible to detect analytical signal with certainty. So analytical signal or the signal that we are interested should be larger than the blank signal by some multiplication, right? Otherwise, we will not be able to detect the analytical signal, right? So normally, the K value at the 95% confidence level, we call this K equals to 3. So the blank signal, when we multiply the blank signal by 3, the analytical signal should be larger than that value. If it happens only, we will be able to detect that analytical signal. So if the analytical signal, intensity of the analytical signal is less than the K times blank signal, then the analytical signal will be hidden inside the blank signal. So that's why we cannot detect it. So that is the reason. So in order to the detection limit is the multiplication of the blank signal by some number K, right? So as the limit of detection is approached, the analytical signal and its standard deviation approach the blank and its standard deviation. So blank plus K values of the standard deviation. this number equals to the analytical signal. This is the equation that we can use to find the detection limit. Blank signal plus k times the standard deviation. So this k value, when k equals 3, the confidence level of detection will be 95% in most cases. So therefore, we can substitute 3 at the 95% confidence level. We can substitute 3 for the k value, and when we know the standard deviation of blank and when we know the blank signal, 3 times standard deviation plus the blank signal, that is the minimum signal of the analyte, so which means the detection limit. So that is how we can calculate the detection limit. And once analyte signal and blank signal is determined, detection limit can be determined. So here, by using this equation, we can determine the analyte signal, right? Then when we know the analyte signal equals to the m times concentration plus blank. That is from the calibration plot. So using that equation, we can calculate the detection limit concentration. So Cm is the minimum concentration. That one we can calculate using the slope of the calibration plot. And then the dynamic range. The dynamic range is the limit of quantification, the region between the limit of quantification to limit of linearity. So limit of quantification means the lowest concentration at which quantitative measurement can be made. So that is the lowest concentration that we can measure quantitatively using the instrument response. Right? The limit of quantification can be higher than the detection limit. So sometimes the detection limit, it is really difficult for us to distinguish, but when it comes to the limit of quantification, that is the minimum concentration at which quantitative measurements can be made, and the limit of linearity is the deviation from the 5% 5% linearity is when the deviation of 5% from the linearity. For example, just think about the UV measurement, and you know in the UV calibration, the Beer's law obeys in between 0.2 to 0.7 region. We always say take the measurement in between 0.2 to 0.7, right? The reason is the less than 0.2, even though still we can see the response, it is not a good quantitative measurement. The Beer's law deviate a little bit. And also after 0.7, still we can take the measurement, but the linearity will be deviated. So that 0.2 to 0.7 region, we can call it as the dynamic range in the UVs. So because it deviates from the Beer's law when the absorbances are beyond that region. Similar thing happens here. So the dynamic range is the lowest limit is the limit of quantification, and the highest limit is the limit of linearity. So when it starts to change the linearity, that is the highest highest margin. And selectivity. Yeah, we have one more slide. I think let's finish that one also. The selectivity is really, really important. When we perform any analytical measurement, So the analyte should have highly selective. So suppose we have analyte A and some other interferences, B, C, other interferences, then the analyte should give the response it should have high selectivity to the response. Otherwise, we will not get the correct signal if both analyte A as well as the interference B also contribute to the signal. Then we will not end up with the correct information. Therefore, the selectivity is highly important. So the selectivity is the degree to which the method is free from interference by other species contained in the sample matrix. So if the method is free from interferences by any other substances present in the sample matrix, we can tell that, okay, this method is highly selective to determine analyte A, right? So this is an example. Suppose sample contain components A, B, C. A is the analyte, B and C are the, let's say those are interferences. So if those two interferences are present, total instrument signal S will be given by this equation. M is the calibration sensitivity and C is the concentration of each and every sample, the components, right? And SBL is the blank signal. So this equation will give the total signal, because even though we measure the A, we will not get a signal free from B and C because those are some interfering reagents. So what we can do, when we determine the selectivity, we can calculate the selectivity coefficient for A with respect to B. So selectivity coefficient of A with respect to B is the slope, the ratio of the slope between the B and A, right? And similarly, we can find the selectivity coefficient of A, which is the analyte, with respect to C also, by taking the slope of these two. And then we can, once we know the KBA and KCA, the selectivity coefficient, we can substitute these values here to that equation, right? So instead of MA, and that is, we will not change it, that is the analyte, slope and the concentration. Instead of slope of B, we can substitute coefficient of B, selectivity coefficient of B times MA. MA is common, therefore I took it here. K times MACB, that is this one, right? Instead of what have been done here, instead of MB, it has been substitute KB times MA, right? KBA times MA. And similarly, instead of KCA, the selectivity coefficient of A with respect to C times MA. And this one will give an idea about, if we know the selectivity coefficients, then we can have an idea about the selectivity of this instrument for the analysis of A. So it is easily we can calculate the selectivity coefficients. So selectivity is also highly important thing when we select the analytical instrument. So sensitivity, selectivity, detection limit, precision, bias, and what is the other one? Dynamic range. So those are the main thing that we should consider when we determine the instrument for the analysis. So we can stop from here. So this question, you can work on that question, and you have to find the detection limit also. Do you have any question? I think it was. Any questions from today's lecture? I quickly go through this one because even though some terminologies are new for you, you already learned these things somewhere. So any question or? Okay, if you have any question, you can email me, and also we will have the next Monday also we will have this lecture. And what I will do, I will create, because I also have trouble with logging to the LMS, so I will create a Google Classroom and send you the email. So, and I'll upload the recording as well as the this PowerPoint presentation. And meantime, if you have any, you can refer this, and if you have any question, just email me. Okay. All right. So hope you all are good. Okay then. Shall we end the lecture, or you have anything to clarify? Do you have anything to clarify?
No, madam.
All good?
Yes.
Okay. Okay then. And then I'll close this one, and maybe if in case when you refer, if you have any question, just email me. And please download, if you don't have the textbook, if you don't have it yet, please download it and go through the textbook. Okay. Okay then, have a nice day.
Thank you, madam. You too.
Okay. Bye.